For Lab 5, Motion of Falling Objects, this is Neha Sinha. The objective of this lab was to observe two objects, one falling rapidly and one falling slowly, and to analyze the forces acting on them. I chose a rubber ball for a rapidly moving object, and a cotton ball for a slowly moving object. Here in Tracker is the rubber ball. I used this picture frame for calibration. The origin was placed at the starting position of the ball, which traveled along the negative y-axis, in line with the end position of the ball. The time step was 0.034 seconds. The red dots mark average location of the ball at each iteration. The same is true for the cotton ball. Note that both of these videos begin when the ball enters the frame and end when it leaves the frame. Neither start from rest, which, as you will see, is later adjusted for. The rubber ball is 0.23 kilograms and starts at the origin. It does not start from rest, so I use the data from Tracker to find the initial velocity, which is the difference in position of the first two frames over the time step. The velocity ends up being negative 3.44 meters per second. The time steps I use in Python is 0.034 seconds, because that is the time step applied to the Tracker data. Here's the Python model for the rubber ball. The cotton ball has mass 0.001 kilograms, or 1 gram. I did the same thing to calculate the initial velocity, and the time step is the same. Here's the Python model for the cotton ball. To make these models in Python, Newton's second law was used. Gravitational force is the mass times gravitational acceleration. Drag force is given by the formula here. Net force is the sum of these two forces. To update position and velocity, the momentum principle was applied, as seen here. Here's the updated velocity and here's the updated position. The same was done for the cotton ball. Note, for the rubber ball, drag force is 0. This is because the observed data, in blue, matches up with the model data, in red, without drag force, indicating little to no drag force existed in the observed data. For the cotton ball, excluding drag force produced this model. Clearly, they do not match up. So, the proportionality constant b had to be adjusted until the model fit. Increasing b to a number too high produced a model with too much drag that does not fall quickly enough. This model can be seen here. The correct b ended up being 0.16. With this value, the observed and model data matched up well. For the what does it mean question, it asks which model predicts terminal velocity, the one with no drag force or the one with drag force. Clearly, it is a model with drag force. Velocity is the slope of position in time, and it can be seen that this graph has a constant slope, indicating constant or terminal velocity. The two cotton ball models, one with drag force and one without, have velocity as a derivative or slope at each point. Without drag force, velocity as a function of time is continuously changing. With drag force, it reaches terminal velocity. The what if question asks what will happen if the object is thrown down, rather than dropped from rest. If you recall, though my objects were dropped from rest, the tracker frame began when they had an initial velocity greater than 0. A similar thing would happen if the object was thrown down. It would simply have an initial velocity greater than 0. The object would still hit terminal velocity at the same velocity as it did when dropped from rest. Of course, a model without drag force, like this one, would not indicate terminal velocity. Thank you for listening.